Good morning, everyone. I am Prasanna Kumar from CSM Section C, and today I'll present on special coordinate transformation for thermal energy distribution in special pressure vessels. Thermal energy distribution inside a pressure vessel is very important because affects it directly affects safety, performance, material durability, and failure prevention. Traditional coordinate systems like Cartesian sometimes fail to represent complex shapes accurately. This is where special coordinate transformations help us analyze heat transfer more precisely. Importance of transformation. Coordinate systems simply complex geometries and boundary conditions. They enable more accurate modeling of heat flow in irregular vessel shapes. Proper transformations lead to better thermal management strategies. Coordinate transformations help simplify complex geometries when vessels like curved or irregular shapes. Applying transformations allows us to convert them into simpler shapes where equations become easier to solve. This results in better heat flow modeling, more accurate temperature prediction, improved design and safety strategies. The transformations act as a bridge between real world geometries and mathematical analysis. Types of pressure vessels. Common pressure vessels include cylindrical, spherical, and elliptical types. Each shape represents unique challenges for thermal analysis. Customized coordinate systems can improve the analysis for each vessel type. Pressure vessels come in several shapes, such as cylindrical vessels, commonly used in boilers, pipelines; spherical vessels, used in gas storage; elliptical vessels, used when compact design is needed. Each of these shapes affects how heat flows inside the material. Thus, each shape needs a different coordinate system for effective thermal modeling. Basic principles of coordinate transformation. Coordinate transformation maps a complex geometry into a simpler computationally manageable domain. The transformation involves mathematical functions relating original and new coordinates. Ensuring the Jacobian determinant is non-zero is critical for valid transformations. Mathematical foundations. The transformation functions are typically derived from differential geometry principles. The Jacobian matrix captures how different elements change under transformation. Proper Jacobian calculation ensures conservation of physical quantities like energy. The foundation of coordinate transformation comes from differential geometry. The Jacobian matrix tells us how small areas, volumes, or lengths change when coordinates are transformed. It ensures that physical quantities like thermal energy, heat flux, and material integrity remain conserved during analysis. Without correct Jacobian calculations, thermal modeling becomes inaccurate. Common coordinate systems in thermal analysis. Cartesian coordinates are straightforward but limited for curved geometries. Cylindrical and spherical coordinates are often used for regular vessel shapes. Specialized transformations extend these systems to more complex geometries. For thermal analysis, we generally use Cartesian coordinates for simple rectangular shapes, cylindrical coordinates for pipes, boilers, and reactors, spherical coordinates for spherical tanks and gas vessels. However, real world vessels often have custom shapes, so specialized coordinate transformations are needed. Need for special coordinate transformation. Standard coordinate systems may not accommodate irregular vessel features. Special transformations can handle non-uniform thickness and asymmetric features. They improve the fidelity of thermal energy distribution models. Standard coordinates are not enough when vessel walls have non-uniform thickness. There are asymmetric features. Geometry is irregular or complex. Special transformations allow us to fit the coordinate system exactly to the physical shape, making thermal simulations more accurate and reliable. Example: transformation for cylindrical vessels. Cylindrical coordinates r, theta, z. Simply analysis for simplify analysis for symmetrical vessels. Transformations can be applied to include elliptical or compressed shapes. These adaptations help in accurately simulating heat flow in the real-world vessels. Cylindrical coordinates r, theta, z are used when vessels are perfectly cylindrical, but in real life vessels may be slightly elliptical, compressed due to stress or irregular due to manufacturing. Special transformations modify the cylindrical system to fit these variations. This makes heat distribution simulation more realistic. Transformation techniques for elliptical vessels. Elliptical geometries require conformal mapping to standard shapes. Techniques like Schwarz Christoffel transformation are employed. These mappings facilitate analytical solutions of heat equations. For elliptical vessels, conformal mapping techniques are used. One popular method is Schwarz-Christoffel transformation, which transforms complex elliptical boundaries into simpler geometries. These transformations help us to solve heat equations analytically, which is different in irregular domains. Applying the transformation to heat equations. Transformed coordinates modify the partial differential equations governing heat transfer. The heat equation becomes more manageable in the new coordinate system. Boundary conditions are also transformed accordingly. Numerical methods in transformed coordinates. Finite element and finite difference methods benefit from coordinate transformations. Mesh generation becomes more efficient in the transformed domain. Numerical stability improves with appropriate transformations. Numerical techniques like finite element method (FEM), finite difference method (FDM) become more efficient when used in transformed coordinates. This is because mesh generation becomes easier. Numerical stability improves. Computational cost decreases. This directly leads to faster and more accurate simulations. Case study: cylindrical to spherical transformation demonstrates how a cylindrical vessel's heat distribution can be analyzed in spherical coordinates, simplifies boundary conditions for certain symmetric heat sources. Results shows improved accuracy in thermal modeling. In some cases, analyzing a cylindrical vessel using a spherical coordinate transformation can simplify boundary conditions. For example, if heat sources are centrally located, if symmetry can be exploited, if the vessel needs a spherical approximation. This case study shows how transformed coordinates can lead to more accurate thermal predictions by reducing analytical complexity. Advantages of special coordinate transformations: enhanced accuracy of thermal energy distribution predictions, reduced computational complexity and simulation time, better alignment with physical vessel geometries. Limitations and challenges: deriving appropriate transformations can be mathematically complex. Not all geometries are amenable to straightforward transformations. Numerical errors may arise if Jacobian calculations are imprecise. However, there are challenges. Deriving transformations can be mathematically complicated. Some complex shapes cannot be easily transformed. Numerical errors may occur if the Jacobian is not computed carefully. Thus, engineers must use these transformations thoughtfully. Practical implementation steps: identify the vessel geometry and boundary conditions. Derive the appropriate transformation functions. Reformulate the heat transfer equations in the new coordinate system. The practical steps includes identifying the exact geometry of the vessel, deriving suitable coordinates transformation equations, reformulating the heat transfer equations, applying boundary conditions, running simulations and validating results. This step-by-step approach ensures accurate thermal analysis. Software and computational tools. Use CAD and FEM software to model geometries and transformations. Implement custom transformation functions within simulation environments. Validate models through experimental data when available. Modern tools help automate these calculations. CAD software for modeling, FEM software like ANSYS, COMSOL, or ABAQUS Custom transformation functions in MATLAB or Python validate with experimental data ensures accuracy in thermal predictions. Future directions in thermal analysis. Integration of adaptive coordination transformations for and evolving geometries, developing of automated transformation algorithms, applicable application of machine learning to optimize coordinate mappings. In summary, thermal analysis in pressure vessels is essentially for safety and efficiency. Special coordinate transformations help simplify complex shapes. They improve modeling accuracy and reduce computation time. Proper application enhances performance and reliability of pressure vessels. This makes coordinate transformation a valuable tool in advanced engineering problems. Thank you all for listening. Thank you.